Um, Hi everyone, welcome to supplementary video 12. So in this video, what I wanted to do was I wanted to basically go through the force calculation for squeeze flow. I kind of felt that we rushed this in the class a little bit today, so just want to make sure that I explain some of the things very clearly, go through the math slowly, and this will hopefully ensure that you have, it's clear that this whole force calculation is clear. So just to briefly remind, this squeeze flow problem is about the setup where you have two. We are squeezing the two circular discs, which are weightless discs with a force Ft, and that's creating the flow into the system. This is a Stokes flow problem, which is nearly unidirectional and which is also pseudo steady. So first thing first, in the lecture, we calculated the pressure profile, which has been written down here. If you have a confusion about this pressure profile, please go back and review the lecture notes and video. But this is something we derived in the class. We first calculate the velocity in the radial direction, and then next we basically utilize the continuity equation to get this pressure profile. For the force balance, basically, I think it was confusing in the class because we want to do a force balance in the Z direction. So that is the very important part I want to emphasize is that look at this top plate, assume that we have the top plate, this plate here, and we're applying the force on the externally using Ft in the negative Z direction. And then there's some force from the fluid on the plate in the positive Z direction because of pressure. And if I was to write this balance on the plate, then I can write this equation m du by dt, which is the mass times acceleration for the plate, is Fpz, which is the positive force, minus negative force, which is the Ft, and this is in the Z direction. So just want to clarify that. And this is equal to 0 because mass is equal to 0. We have been given that the plate is essentially weightless. So because we have been given that, essentially what we wanted to do is to calculate f of t, we want to calculate Fp of z, which is the force by the fluid on the top plate in the Z direction. So that's the goal. So this is, I think, something which was slightly less clear in the lecture. I hope this makes sense now. We applied the force balance on the plate and basically equated Ft with Fp of z. So to calculate Fp of z, first we will calculate Fp, which is on the top plate. And that is basically that is given by stress vector in the normal direction times dA. Okay. And stress vector is nothing but n dot sigma dA. Okay, so we know that, and this is something we know from the previous lecture. The stress vector, where this n is the normal pointing into the fluid. Okay, so here is the normal direction. Normal pointing into the fluid in the top plate is in the minus EZ direction. Okay, so n is minus EZ. Okay, and sigma is we know minus P delta plus tau. Okay, or in this problem, we don't have a theta dependence. We only have an R and Z dependence. So this becomes minus P 0, 0 minus P plus tau RR plus tau ZR plus tau RZ plus tau ZZ. Okay, or this essentially becomes minus P plus tau RR tau ZR. Sorry, I think I wrote these two opposite. And they're both the same, so it's not as important, but just to make sure it's clear. Tau ZR and minus P plus tau ZZ. Okay. It's a symmetric tensor, so R, Z, and ZR doesn't matter as long as the magnitude we calculate is correct, but just to be sure. So this is sigma, and then n dot sigma is so n dot sigma is 0 minus 1. Okay, so n is 0 minus 1 times minus P plus tau RR, tau RZ, tau ZR, and minus P plus tau ZZ. And finally, once you calculate this, you will get minus tau ZR ER plus ER plus P minus tau ZZ easy. So that's the important part. So this is n dot sigma, the same as S of n. Okay, this is what we can calculate. And this is, I think, was a bit rushed in the class. So this is something you will be able to calculate. This is how we do all the force problems, right? We want to calculate the force by the fluid on the plate. And to do that, we did n dot sigma dA. So for first, we calculated n dot sigma. For n dot sigma, we got this result. So there are two components. One is the radial component, and one is the z direction component. And what we want to focus on is the z one. We want to focus on this because we are only interested in fp of z. So this is that's why basically we can say finally f of t is fp of z or is equal to p minus tau zz dA. Okay. And now to calculate p and p minus tau zz dA, we have to find tau zz2. We already have the pressure profile and we have still not found the tau zz component. But to tau zz component, we can first see this, that tau zz is actually equal to 2 mu del Vz by del Z. And this is actually scaled as mu by h because Vz scales as u and delta Z scales as h. Whereas pressure scales as mu u r square by h cube or mu u by h into r by h whole square, right? In other words, tau Zz by p is 1 by r by h whole square. And this is much, much smaller than 1. So this is very common in these systems whenever you have a thin channel that you can ignore the normal component of the shear stress. In a two-dimensional flow, you will see later down, it's actually, you cannot ignore this. But essentially, if you ignore this, you basically get Ft is PdA or finally 0 to R P of R 2 pi R dr. And this is 3 mu u, I guess 3 mu u R square by 4h cube. This is 3 mu u r square by 4h cube times 2 pi r is equal to 0 to, sorry, 0 to r. I had made a small error, 0 to r, 0 to r here, okay, 0 to r, then r into 1 minus r by r whole square dr, okay. So for now, this becomes 3 mu u r square pi by 2h cube, and then this becomes r square by 2 minus r4 by 4r square. And I'm doing this a bit fast because this is simple math steps and you can do this yourself, but these are not very difficult to see. So this is what you get for by integrating the terms inside, or essentially what you get is 3 mu u r square pi by 2h cube times r square by 2 minus r square by 4, or finally you get 3 pi by 8 mu u r is power of 4 by h cube. So this is what we get. Okay, so this is our force of T, and this is what I wanted to calculate. So I wanted to make sure that you get this, you see the whole process coming together clearly rather than a bit of a rushed way. So let's do this again. Let's see what we did again. So we said first, let's say we have calculated the pressure from the squeeze flow, and again you can review the lecture material once to make sure you understand that. Then we said because of the fact that our plate is weightless, we can simply say that the force that we are applying externally is equal to the force by the fluid on the plate. Fp is equal to F of T. To calculate Fp of Z, first we calculate F of P, and for that it is n dot sigma dA. We calculated n dot sigma, which comes out to be tau zr and P minus tau zz. But we are only interested in the zth component because we want to calculate Fp of Z. To calculate Fp of Z, we basically took the zth component and want to integrate that. But because tau zz is much smaller than P, based on order of magnitude analysis, you can simply integrate the pressure. And when you integrate the pressure, you get the result, which basically I've written. And you can see that this is actually very similar to what you have when you do the scaling analysis, you get mu u r to the 4 by h cube. So it's actually very similar to what you will get from scaling analysis. Okay, so hopefully this video was helpful, and I will basically, I look forward to seeing you on the next lecture. Do let me know if there's any confusion. and I'll see you on Thursday.